but with the mutually exclusive other blocks filtered out. This basic block, VHDL backend, can only process sequential code. The state machine, which controls which step it's currently processing, is a shift register using a one-hot coding, which makes the decoder pretty simple. The memory accesses break this shift register, so the whole state machine stops, waits for the data to return, and then continues with another shift register. So the shift register is broken up for memory accesses, if there are any in their basic block. For the instructions in the LLVM, the backend uses a one-to-one mapping for each instruction. In the LLVM, there's a hardware element implemented. This uses quite a lot of hardware resources for bigger blocks. Blocks containing migrate intrinsics are not created. This is different to the software part, where the whole stuff is created. Here, we leave away the stuff running in software. The hardware itself is automatically connected to the PLB bus. This is a bus used by the Xilinx tools and enables a unified memory access. Here we see the VHDL output, little cut out with some sections have been cut out to make it fit on the slide. Here we see the shift register. The numbers show that this basic block has 6 steps going from 0 to 5. There are no memory accesses, so we have only one shift register. We have some data registers holding results, and we see over here we have each clock step. We check, for example, if our shift register is currently driven, and then the hardware instructions are executed. Then here in the part cut out, all the other 5 steps are executed, and then here is the last step. Currently not shown is the driving of the shift register and the whole bus interface stuff and so on. Okay, now with these things in place, there's still the problem that the hardware side has to do some memory accesses. The memory accesses, or the bus interface, has been done by a student of mine, Mark Stöttinger. He implemented it. For each, so we have the LLVM VHDL backend over here. There's a multiplexer, and for each memory access, there's a port created within this entity. With this multiplexer element, we connect it to the PLB slave element, which has access to the PLB bus. We choose to implement it as a slave device for debugging, so we can see memory accesses of the hardware backend. If we are running the hardware, we get an interrupt on the PowerPC, so we can check for correctness. Later on, it's planned to make a master device out of this, so we can have autonomous memory accesses by the hardware itself. Then is the most hackish part of this is the extraction of the memory addresses. Software and hardware have to agree on the memory addresses used, and they have to be transferred from the software side, which has already all the memory addresses included, into the hardware side. So since we're currently running in real mode, we just can extract the memory addresses right off the binary with an M tool, standard binary tool in the Unix environment. We're using the stream editor for merging the extracted the extracted addresses with the hardware backend, and after that, the hardware backend has also the same addresses as the software side. This process is pretty fragile to the reliance on symbol names, and it's currently a work in progress because on some larger examples there's still some corner cases where it breaks. So this is unfortunately not completed. Okay, after that we are down here in the synthesis phase. We have a complete description of the software. We have a complete description of the hardware. And these both are fed into the Xilinx EDK. That's embedded development kit. The EDK design flow is pretty standard. There are only a few exceptions. So the Xilinx interrupt handler was much too slow because it was pretty generic and so on. And so we replaced it with a custom assembly interrupt handler to speed up the memory accesses of the hardware part. This is in turn only needed because we have a slave device. And because we have this custom assembly handler, we have to use our own start files and custom linker scripts in the software design flow, working on the assembly output of the LLVM assembly output. And then a bit stream is created, and this is programmed onto the XUP board. Here are some results of the numbers. You can see over here that we have 3 multipliers and 4 adders subtractors. That's the same as the numbers used in the basic block. Otherwise, besides of these, we have pretty lean resource usages.